Now let's see what happens inside the resistor. So let's say you have a battery with the plus side on the left and the negative side on the right. And that means it'll make some kind of current in the circuit going this way. And this side will be at a higher potential than this side. So the electric field inside the resistor will be going from the left to the right. Now, if you take any negative charge, any electron inside the resistor at a certain time, it's going to move opposite the electric field. Now, inside the resistor, there's no source of EMF. There's nothing to force the charges to go opposite the direction they want to go. So the charges will just move in the direction of the force applied on them, which is to the left. And so they'll start to move with some average speed v drift to the left. So if you take the energy of the charge field system, when you're thinking just about this one charge to be the initial value u initial, and you wait a certain amount of time delta t, the charge will move a certain distance delta x to the left. And the final energy will be less. The negative charge, when it goes opposite the electric field, the potential energy of the system gets less. And we can then see that the difference in potential energy between the two configurations is the charge times the potential difference. Now the charge is minus E, and the potential difference, the potential here is bigger than the potential here, because the electric field goes from high to low. So delta V is positive. So to make sure we know it's positive, we'll write a positive here and we'll take the magnitude of delta x so that there's no confusion that if this is positive or negative. So it's similar to what we did before with the battery. Now, if you want the total change in energy due to all the movement of all the charges, because inside the resistor there's not just one electron that's moving, being affected by the electric field. There are many electrons, n free electrons that can move. And so we do the same thing as before. Not each electron has to move the same distance because the electrons inside the resistor, they move in a very random way. But if we think about the average motion, we can say on average the electrons move some distance delta x average. Same argument we did before in the case of the battery. So we can say that the difference in energy between the two configurations is the number of charges, free charges, times the charge of each charge, times the potential difference between 2 points where you're taking the average distance that the charges move through. So now if you write everything out, and the minus sign comes out here, and n, as before, it's the number of charges per unit volume times the volume, and the volume is A times L. And so we can change L, n, and write instead of it small n times A times L. And exactly as we did before, we want to get now the rate at which the energy changes. So you take delta U by delta T. So here we have delta X average by delta T. This is again the drift speed. This is just the speed of the average speed of the charges as they move inside the resistor. So we can replace this by V drift. And we get this equation. So we have the minus sign, and we have this expression again is just the magnitude of the current, and this term is the potential difference between E times L is the potential difference between the two sides of the resistor, the two ends of the resistor. The minus sign, it means that the energy is getting less. If you wait for an amount of time delta t, each charge loses some. The system loses some potential energy when the charge moves from one point to another, and so the amount of energy difference, the difference in energy is getting smaller of the charge field system. And so you can write down then the power, which is the rate at which the charge field system loses energy. It's minus I delta V, where delta V is positive. It's the potential at A minus the potential at B. So we get a similar result as we had before. It's the current times the potential difference, but here we have a minus sign saying that the energy is getting lower. So where does the energy go? If the energy is getting lower, the energy must go somewhere. So imagine, if you think on a molecular level, what's happening. If the electric field is pointing to the right, the charges move to the left. As the charges move, they hit things, they hit other electrons in their path. So they can't really actually move easily inside this material. They keep on hitting things. So they gain some kinetic energy, they lose potential energy, and then they lose this energy to the atoms inside the resistor. And so the atoms, the energy of the atoms gets bigger. And so the internal energy of the resistor gets bigger. And that leads to an increase in the temperature of the material. That's why resistors are very hot. When you put a large current in them, the resistors get very hot. So we can write down the power, as we said. Now this is writing it as the amount of energy that's gained by the resistor as internal energy. So it's a positive value. The resistor itself is gaining internal energy. The energy is getting bigger. What's the rate at which the internal energy of the resistor increases? It's the current times the potential difference. Now, what can we can write this formula in a different way. What can we replace delta V by? We can replace delta V by I times R. And so you can get another equation for the power, which is I squared times R. Or you could replace the current by delta V over R. And so you get delta V squared over R. And so these are just different ways of writing the power. So you have three different ways to write the power that's gained by the resistor. The rate at which energy is gained by the resistor, the internal energy. You can either write it as I delta V, I squared times R, delta V squared over R. The units of power is watts,